We are beginning a new unit called Electrochemistry. As I was explaining, you would have downloaded and studied a presentation called the Redox Review, and also a document on electricity from our Canvas site. I'm not going to discuss those things, and you should be able to go back and review the rules for determining how do I establish the oxidation state of the different elements in a compound. What we're going to study today is how to properly balance a redox equation. Remember, in an oxidation reduction reaction, which we sometimes abbreviate as redox reaction, one substance loses electrons, one substance gains electrons. The first process, we call it oxidation, the second one reduction. And the way we can tell if a reaction is part of this category of redox reactions is by looking at the equation and calculating if any of the reactants changes the oxidation state as they proceed from reactant to product. So let's consider the oxidation of iron 2 to iron 3 by this polyatomic ion called the dichromate ion in an acid solution. In redox equations of the kind that we study, we're going to do them in solution, and it will be important to notice if it's acidic or basic solution. First thing we have is the unbalanced equation for the reaction in ionic form. In other words, we typically write out the net ionic equation. Normally, in any given problem, this is where it will start. They'll give you the unbalanced equation, and it is up to you to work it from here. In this case, it is obvious that the iron 2 is being converted to iron 3 is being oxidized. Sometimes you will not be able to tell just from looking at the equation who is getting oxidized and who is getting reduced. But what will happen is that the process of balancing the redox equation is going to reveal to you which one is getting oxidized and which one's getting reduced. So what we're going to do first of all is we're going to separate the equation into its two half reactions. Again, in this case, it's fairly obvious to see that the iron 2 to iron 3 conversion is the oxidation one. You can see where the oxidation states go from +2 to +3. That means that the reduction half then is the conversion of the dichromate ion into chromium, and you should be able to calculate the oxidation states in that case as chromium going from +6 to +3. Since it's decreasing the oxidation state, that means getting more negative, therefore it's getting reduced. So this is where we start. Now, our next step is going to be to balance out all of the atoms that are not oxygen and not hydrogen. We're going to balance oxygens and hydrogens in a peculiar way, so we start out with the other atoms. In this case, the iron is already balanced with it. There's one atom on each side. However, for the reduction half reaction, there's two chromiums on the left and only one on the right. So we'll balance that by putting a coefficient of 2 next to the chromium 3 ions on the product side. Okay, give you a chance to catch up and write those out. Okay, our next step now is to balance out oxygens and hydrogens, but like I said, we're going to do it in a peculiar way. We're going to balance oxygen atoms by adding water molecules. And then we're going to balance hydrogen atoms by adding protons or hydrogen ions. In the case of the iron oxidation, there's no oxygens to balance, so we don't do anything there. But in the case of the reduction, we see that there are 7 oxygens on the left side. So we're going to add 7 water molecules on the right to give us the 7 oxygens. Notice that when we do that, we are also adding 7 times 2 or 14 atoms of hydrogen. The way we balance those is by adding 14 hydrogen ions on the left side of the equation, and that gives us this equation here. Please check again, make sure that you understand what we did. Again, we added waters to balance the oxygens, and then we added hydrogen ions to balance the resulting hydrogen atoms that were on the right side. Now, because these are oxidation reduction reactions, electrons have to be involved. So our next step is we're going to add electrons to one side of the half reaction to balance the charges overall. This is the step where if you did not know at the beginning who was getting oxidized and who was getting reduced, this is where it's going to show. Okay, for the oxidation half reaction, we see that in going from +2 to +3, iron has to lose an electron, so we're going to put it there on the right side. And you can see that by putting the electrons on the right side as something that's released, we know that this substance lost electrons, therefore it got oxidized. So as you can see, the process revealed to us who was the oxidation half reaction here. Now, in the case of the reduction half reaction, we have an issue because we have 14 positive charges here. We have a -2 charge there, and then we have 2 times 3, which is +6 charges on the right. So if we have +6 on the right, and on the left we have 14 minus 2, right, which is 12. Well, that means that we have an excess of 6 positive charges on the left side. Let's offset them by adding 6 electrons, 6 negative charges. And once more, this step reveals that this is the reduction half reaction because electrons are coming in, electrons are being added. Now, the overall equation is the combination of the two half reactions. But before we add them, we had to make sure that the electrons will cancel out. So that means that we're going to have to equalize the number of electrons by perhaps multiplying one or both half reactions by an appropriate factor. In this case, we see that the reduction half reaction requires 6 electrons. But at this point, the oxidation half reaction is only supplying 1. So what we're going to do then is we are going to take that top one and we are going to multiply not just the electrons but the whole thing times 6 so we can get the proper arrangement here. So we've multiplied the oxidation half reaction by 6. We leave the reduction half reaction as it is, and therefore we have a set of half reactions that we are ready to add now. Let me give you a few seconds to write that down. Okay, so now we're ready to add them. The important thing here is that as we add the two half reactions, the electrons on both sides must cancel. And we still need to make sure that the final equation we get makes sense. So here is our oxidation half reaction, which has already been adjusted to compensate for the number of electrons required. Again, remember, we had to multiply the whole equation, not just the electrons. And this is the reduction half reaction. We're going to add them up. As we see, the 6 electrons on the right side of the oxidation will cancel out with the 6 electron on the left side of the reduction. And so when we add up the equations, we get this final equation here. It's very important when we do this, at least until we get a little more experience, in our portfolio here, right? That we make sure that everything squares off. For example, do all the atoms balance out? So I have 14 hydrogens on the left, and then I have 7 times 2, that's 14 on the right. Okay, that checks. I have 2 chromium atoms on the left, 2 chromium atoms on the right, check. I have 7 oxygens on the left, and via the 7 water molecules, I have 7 oxygen atoms on the right. And then I have 6 irons on both sides. So we're good as far as atoms are concerned. We also want to make sure the charges are balanced. So on the left side, we have 14 plus, we have -2, and then we have 6 times +2. That adds up to 24. Should be the same on the other side. So on the right side, we have 6 times plus 3, 2 times plus 3 for a total of 24. So that checks. And therefore, that equation that we just did here, it is the correct equation. We have it in there. The only thing that would be missing is, if required, we would have to put in the proper physical states in this case. This is the redox equation for this reaction in an acid environment. Notice that there are protons in there. In some cases, the protons are going to show up on the reactants side. In some cases, they're going to show up on the products side. If the reaction were carried out in a basic solution, what we do is we carry out the process all the way to here as if it were a acidic solution. And then what we're going to do is we are going to add hydroxide ions to both sides of the equation, one hydroxide for every H plus, so that when you combine them, the hydroxides and the hydrogens become water molecules. Okay, I have a few practice exercises for you. For those of you who were able to be in the live session, we worked on one of them. What I'm going to be doing here is I'm going to post that whole worksheet on our Canvas page, as well as 3 other practice exercises for you to do on your own. Unfortunately, because of time constraints, I'm not going to work through that problem again here on this video, but you should be able to follow along with the documents that I'm going to be posting on our Canvas site. All right, so we'll be back after this break to discuss how do we use redox reactions to generate useful energy.